Hi, I'm Hamish. I'm a second-year PhD at EPFL, and today I'll be presenting work done jointly with my colleagues in the lab. So memory makes up a large proportion of the cost of modern servers, but at the same time is important for performant analytics. And in this talk, we are going to show that analytics on modern hardware can be memory efficient. There we go. Systems for fast analytics are built on assumptions that are not necessarily true with modern hardware. First, as DRAM prices have dropped over the past decades, there was a tremendous amount of productive work on in-memory systems for high-performance analytics. However, as the pricing of DRAM has plateaued and DRAM is now one of the most expensive components in servers, it is no longer cost-effective to use memory as primary storage. Second, historically for caching stores, maximizing cache hit rates in order to minimize disk accesses has been key to performance due to the large gap in performance between memory and storage in the past. However, for analytics, with its heavy sequential access patterns over input data, bandwidth is more important than latency. And thus, as the bandwidth of arrays of NVMe drives is now competitive with memory bandwidth, cache misses are no longer necessarily a death pill for performance. Additionally, in the past, the impact of NUMA effects has been treated as inconsequential relative to the high cost of disk accesses. However, with increasing NUMA heterogeneity, for example, with GPU-equipped servers, we have varying query processing throughput, memory capacity, and bandwidth to storage across different devices within the same server. Thus, the choice of which memory is used for caching now has an impact on performance. And to make the best use of high bandwidth storage and accelerators, the storage layer needs to be both workload and hardware aware. So heterogeneous servers do not have a linear storage hierarchy. Instead, we have a hierarchy with multiple types of compute devices and more than one way to move the data to them. So we have multiple transfer paths, which we can characterize by their bandwidth and minimum transfer granularity. First, the CPU can, of course, still access the byte addressable DRAM at the low hundreds of gigabytes a second. Likewise, the GPU can access its own local memory, but at the high hundreds of gigabytes per second, or even low terabytes per second on state-of-the-art hardware. And we have two ways to move data from DRAM to make it accessible by the GPU. We can eagerly move pages from DRAM into the GPU memory, where the GPU can then access it directly, or the GPU can also bypass its own memory and directly access the byte addressable DRAM. But both of these transfer paths are limited by the interconnect bandwidth at about 32 gigabytes a second. For storage, we can move blocks of data from our array of NVMe drives into DRAM, and on our particular setup using a number of NVMe SSDs, we can do so at 86 gigabytes a second. For the GPU, we can move data from the NVMe drives into DRAM, bypassing the CPU memory, but in this case, we're limited by the interconnect bandwidth again at 32 gigabytes a second. And so we have these different transfer paths. We need to optimize based on the workload for which transfer path to use based on the bandwidth and granularity of the paths. So let's first zoom into the bandwidth axes of data transfers. For CPU execution, the read bandwidth of an array of NVMe drives can saturate the CPU processing throughput. We can see this here on the left as we plot the execution time for two star schema benchmark queries executing on the CPU with NVMe resident data. And on the x-axis, we vary the storage bandwidth by controlling the number of drives that we stripe the data across. And on the y-axis, we plot the execution time in seconds. And we pick two queries from the star schema benchmark. We pick a more data-intensive query and a more CPU-intensive, more processing-intensive query, sorry. And so the processing intensive query is going to be spending more CPU time per byte of input data than the data intensive query. And so we can see that for the processing intensive query, it needs relatively little storage bandwidth in order to approach the in-memory performance. And we're plotting the execution times of these two queries when the data in these dashed lines here. And so for the data intensive query, we see that we need quite a lot more storage bandwidth in order to approach in-memory execution. And so what this means is that with workload-aware caching, when we can distinguish between the more processing-intensive and more data-intensive queries, we can preferentially cache data for the more data-intensive queries, which benefit from having higher effective bandwidth to their inputs, and avoid caching data for the processing-intensive queries, which don't benefit as much. Now, on the right, we're plotting the same experiment, but using GPU execution over NVMe resident data. And here we can see that both for the data-intensive and the processing-intensive queries, that the execution times for both of these queries improves as we have increasing storage bandwidth, but only up until we hit the interconnect bottleneck. As after this point, both these queries are bottlenecked by moving data across the interconnect. And so what this means is that for the GPU, we need caching to interconnect bottleneck rather than to make up for slow storage bandwidth. And the caching problem for GPUs is further exacerbated by the relatively high query processing throughput of GPUs relative to their low memory capacity. And further, the query that is processing intensive on the CPU is effectively data intensive on the GPU. And so we can't distinguish between intensive and processing intensive queries, which enables us to do workload-aware caching on the GPU. And so while we can directly transfer blocks of data from the NVMe devices to the GPU, it's not necessarily the most efficient use of the interconnect. So here we are visualizing GPU execution of a query pipeline where we want to select the values from column C, which pass predicates on columns A and B. And we have our table with 3 columns in yellow on the left, which is initially NVMe resident. And as we begin executing, in this example, we can move and process 3 blocks of data per unit of time. And as we begin executing, we need to move all of the data onto the GPU to process it. And this is going to take us 4 units of time because we're bottlenecked by the interconnect. So we propose a new NVMe to GPU transfer method where we also leverage DRAM. And we call this stage semi-lazy transfers. So on the slide, we have the same setup as before with the same query and same data, but we have the addition of DRAM here in the bottom left. Now, in this query, notice that we don't actually need to touch all of the values in our table. We need to access all of column A in order to apply the first predicate, but we only need to access the values in column B and C, which pass the earlier predicates. So when we're processing with NVMe resident data, we can't just skip the bytes we don't want from these columns because NVMe devices are block level devices, and we have to load and transfer entire blocks. However, we can use memory as a staging ground for transfers. So with stage semi-lazy transfers, we eagerly transfer blocks of data that will be used in their entirety, and we stage blocks that will be selectively accessed into the byte addressable DRAM. And then during GPU execution, the GPU can directly access the values it needs from the CPU memory, reducing the amount of data that needs to go over the interconnect and overall improving query processing. So we've effectively moved the cost of overfetching to our NVMe to DRAM transfers and leveraged the high bandwidth between the NVMe and the DRAM to mitigate the lower bandwidth between both of these storage media and the GPU. And the rest of my animation. So because the transfer path depends on both the workload and the hardware, we can't have our scan operator blindly scan the data and guess which memory to load it into, only for later operators to move the data into a more appropriate memory execution. So here on the right, we have a query pipeline executing a scan filter aggregate query. In the bottom right, we have our data, our NVMe resident data, and on the top right, we have the current contents of our cache, where we have one page from the first column of the GPU, and we have 3 pages, one from each column in DRAM. And so at the bottom, we have our operator, we have our scan operator, which emits row groups made up of a page from each column, which are then routed to either the CPU pipeline in blue or the GPU pipeline in green. And then we have the memmove operator that ensures that the data is in the most appropriate memory location for the rest of the pipeline to proceed. And these operators were introduced by HetExchange and originally designed for execution over hybrids of CPU and GPU. And so designed to route and handle page handles that refer to a single in-memory page. And we extend on this design in 3 key ways. First, we have the scan operator emit logical page IDs that are backed by a NVMe resident page and potentially also have in-memory copies of that page, either in DRAM or in the GPU memory. And then we modify the router operator to route to either the CPU or the GPU pipeline instances based on the contents of the cache. So in this case, we have one page for this row group already in the GPU memory, and so it will be routed to the GPU pipeline instance. Then the memmove consults with HetCache on the location of any in-memory pages and the preferred location to cache any newly transferred pages, if any at all. So in this case, memmove is going to take a reference to the first page, which is in GPU memory, and avoid doing a transfer, and load the pages for columns B and C into DRAM where they can be directly accessed over the interconnect. Then after the pages are loaded, the memmove will also register the newly transferred pages with HetCache, which determines whether to admit the pages to the cache. Then the rest of the execution remains unchanged. We apply our filter, we have our aggregate, and then the results are sent back to the CPU to be combined with the outputs of the other pipeline instances. And I won't show the rest of the query execution in these examples because in our design, the rest of the query execution remains unchanged after the data transfers. Now for our second row group, the data is already in CPU memory, and so it's routed to the CPU instance. For our third row group, there is no data in the cache, so it could go to either the CPU or the GPU pipeline instance. In this case, it will be moved to the GPU. And this time, when the pages are registered with HetCache, it admits the pages to the cache. And finally, for our last row group, it again could go to either pipeline instance, and this time will go to the CPU, and the memmove will load the pages into DRAM from the NVMe drives. So we evaluate our design on a AMD machine with an NVIDIA GPU and 12 PCI 4 NVMe SSDs, and we implement it inside of Proteus using the star schema benchmark queries to evaluate on. So firstly, we show the performance benefit of utilizing multiple transfer paths by staging NVMe resident data in memory. So here we run 2 star schema benchmark queries on our GPU, and we report the execution time in seconds on the y-axis. And we use queries 3.1 and 3.4 because they're 2 very similar queries that have a number of hash joins, and so they don't need to access every value from the non-join key columns. They do, however, differ quite substantially in their selectivity, where query 3.1 has a selectivity of 3.4% of the tuples, whereas query 3.4 selects 0.007% of tuples. And so here, the solid bars are showing the execution time when we use eager transfers directly from the NVMe drives to the GPU, and the diagonally striped lines are using the semi-lazy transfers, where the first column is eagerly transferred to the GPU and the subsequent columns are first staged in DRAM to be directly accessed. And so we can see that when we have very selective queries such as 3.4, we can achieve up to a 45% increase in execution time. And so with workload-aware data placement and hardware-aware data transfers, we can achieve more memory-efficient analytics with hybrid CPU-GPU execution. So here we're executing 2 benchmark queries, this time using both the CPU and the GPU for the execution. On the left, we have query 1.3, which is a more data-intensive query. On the right, we have 3.1, which is our more processing-intensive query. And in the solid yellow bars, we have the execution time when the data is initially entirely NVMe resident. In the dashed blue lines, we have the execution time when the data is initially entirely in DRAM. In the diagonally striped lines, we have the execution times when we use HetCache, which is utilizing both the staged semi-lazy transfers and is taking into account the storage bandwidth and the workload bandwidth to place the data. We can see that for the processing, for the data intensive 1.3, that it uses more CPU memory in order to get within a couple of % of purely in-memory execution, whereas for our processing intensive query 3.1, with just a little bit of GPU memory, we can get the same execution times as purely in DRAM processing, but without storing any data in DRAM at all. So to conclude, as storage bandwidth is a DRAM bandwidth, we can achieve near in-memory performance on larger than DRAM datasets through workload-aware data placement that takes into account both the processing throughput of the workload consuming the data, as well as the selectivity of the data accesses. We can also achieve faster GPU execution over NVMe resident data by leveraging DRAM to get the best of byte-addressable DRAM and the NVMe capacity by staging the selectively accessed in DRAM. And finally, the future of storage system design must look down to the hardware and up to the workload in order to make the best use of hardware resources. Thank you.